Hello everyone, my name is Severin, and now that we've covered some of the basics of AP Physics 1, Unit 1 Kinematics in the first video, let's go over a few problems and actually apply this knowledge to some problems you might find on the actual exam. So the first one here is Bernard throws a ball horizontally off a cliff at 15 meters a second. How far does the ball travel before hitting the ground 20 meters below? So we can draw this out with a little diagram here. The ball is 20 meters off the ground and it's thrown at 15 meters a second. And so typically we will solve for distance by multiplying velocity and time, but we don't have time currently, so we need to solve for time somehow. So we can use one of our kinematics equations to find out how long it takes the ball to fall this 20 meters, because we know acceleration due to the Earth's gravity is 9.8 meters a second squared, meters per second squared. So final position equals initial position plus velocity initial times change in time plus 1/2 acceleration change in time squared. 1/2 times acceleration times change in time squared. So if we set the ball's initial vertical position to be 0, then its final position when it hits the ground will be -20, because it'll fall those 20 meters down to the ground. So -20 meters equals, and then as I already said, the initial position will be 0. The initial vertical position is 0. And then remember that the different components of an object's movement, the different components of its velocity, are exclusive from one another. So the ball has a horizontal velocity, but in the moment before it begins moving, it has no vertical velocity. So this is going to be 0, making this entire term 0. So -20 meters equals 1/2 times acceleration is -9.8 meters per second squared times change in time squared. So now 1/2 times -9.8 is -4.9. So -20 meters divided by -4.9 meters per second squared equals change in time squared. So now let's just find -20 divided by -4.9 is just going to be the same as 20 divided by 4.9. You'll get a positive result. And so we get that change in time squared equals 4.08. So we can just take the square root of this. I'll just take it directly from the calculator here. So we get the change in time equals 2.02 seconds. And now remember, we need to find the distance that the ball covers in the horizontally, how far it moves. So we basically just multiply the velocity by the time here. So 2.02 times 2.02 seconds times 15 meters a second is 30.3 meters. So this is our solution. So our next problem here is going to be: an archer shoots arrows from a bow approximately 1.5 meters off the ground. Arrow A flies into the air at an angle of 30 degrees from the horizontal, and arrow B at an angle of 60 degrees from the horizontal. Both arrows have a velocity of 30 meters per second at launch. First, we'll compare the arrows' displacements. So let's just draw out some diagrams here. So we have arrow A, and it's launched 1.5 meters off the ground and 30 degrees from the horizontal. degrees. And both arrows have a velocity of 30 meters per second. And then arrow B is also launched 1.5 meters off the ground, but at an angle of 60 degrees. 30 meters per second, 60 degrees. We have to find the displacements of the arrows. We can do this by finding the horizontal distance that they travel. So first, just like in the last problem, the only way that we could find horizontal distance traveled is finding the time it took to travel that distance, because we don't know the time that the arrows are in the air. So what we need to do is use the same kinematics equation and then plug all the variables into it. So remember, the arrows here are traveling in 2 dimensions. So we have to decompose these vectors and find the arrow's horizontal and vertical velocities. So for A, we're going to have a horizontal velocity of 30 times cosine 30 degrees meters per second. And then we'll have a vertical velocity of 30 times sine 30 degrees meters per second. And then for B, it's going to be the same 30 cosine 60 degrees meters a second, 30 sine 60 degrees meters a second. And so if you remember trigonometry, you know that we can just find simplified versions of these. So cosine of 30 degrees is square root 3 over 2. So this is going to be 15 root 3. Sine 30 degrees is 1/2. So this is going to be 15, well, meters per second, but we can just carry the units down here. And then it's just going to be flipped for arrow B. So this is going to be 15 meters a second, and then 15 root 3 meters a second. Okay, now we can plug these in to this kinematics equation here. So for A, so we have to know the final, or we have to know the final and initial positions. So the arrows start 1.5 meters off the ground. So we can do the same thing that we did in the last problem and say our final position is going to be negative 1.5 and initial position will be 0. So for A, negative 1.5 is going to be our final position equals, and then 0 is our initial position, so we'll just leave that out. But now we have an initial velocity. So this is going to be initial vertical velocity. Everything here is going to be vertical. We're just finding out how long it takes for the arrow to move up and then back down to the ground. So the vertical velocity of arrow A is going to be 15 meters a second times change in time here. And then we have 1/2 acceleration. So acceleration due to gravity is negative 9.8. So times 1/2, negative 4.9, change in time squared. And we repeat the same process for B. So B is negative 1.5 meters equals, and then remember for B, the vertical velocity is 15 times the root 3 meters a second. 15 times square root 3 meters a second, change in time, minus, and then same as A, negative 4.9, change in time squared. So now we use the quadratic formula to solve these. Negative B plus or minus the square root of B squared minus 4AC all over 2A. So B is going to be 15, and then plus or minus the square root of 225, which is just 15 squared, minus 4AC. So C is going to be 1.5, because we can move this over to the other side of the equation here, plus 1.5 meters, and then this just becomes 0. And we'll do the same here. So 4 times 1.5 is 6, and then A is negative 4.9. So we have a negative times a negative, so positive, and then 4 times C is 6, A is 4.9, and then all of that over 2A, so negative 9.8. And B is the exact same thing except with 15 root 3 for the value of variable b. So then we have 225 times 3 plus 6 times 4.9 all over negative 9.8. And now we plug these into the calculator and let's see what we get. So, before we do that though, when you solve a quadratic equation, you have two possible answers, but there's only going to be one answer for this question here. And so in order to determine the right one, we can look at the signs of the numerator and denominator. So the time in this context can't be negative. So that means the numerator has to be negative because the denominator is negative. So the fraction will be a positive number. So we can do, let's say, negative 15. And then let's say we do plus, let's do positive. 225 plus 6 times 4.9. And we get a positive result here. And that means if this is, the numerator will be positive in this case, and then we'll be dividing by negative, so time will be negative, which isn't possible in this case. So what we have to do is we have to do negative 15 minus the square root of 225 plus 6 times 4.9. Okay, so now we get a more reasonable answer here. So we can divide by negative 9.8. Okay, so for A, we get the time. I'll write this down here. 3.16 seconds. And for B, negative 15 times root 3 minus square root of 225 times 3 plus 6 times 4.9, and then divided by negative 9.8, 5.36. And these are our solutions for the times it takes for the arrow to fall back to the ground. But we're not done yet. Now we have to multiply these times by the arrow's horizontal velocities. So I'll just rewrite some of the stuff here on it. I'll just rewrite some of the stuff here on the next page and make it easier. Now that we have the times, we just need to multiply these by the horizontal velocity. So we can recall that horizontal velocity for A is 30 times cosine 30 degrees. And for B, it's 30 times cosine 60 degrees. So 15 meters a second for B, 15 root 3 meters per second for A. And now we can just multiply. So displacement of A equals 3.16 seconds times 15 root 3 meters a second. And then B, displacement of B, or not displacement, but distance traveled horizontally. Which I guess you could say is horizontal displacement. Okay, so 3.16 times 15 times square root 3 5.36 times 15, 88.4. Okay, so you might think we're done here, but I sort of gave it away when I said I couldn't call this displacement, because this isn't actually displacement. The arrows also fell 1.5 meters, so we need to use the Pythagorean theorem to find the actual distance that they traveled from the 1.5 meters above the ground to falling 1.5 meters, but also traveling this distance horizontally. So we'll just do the square root of 1.5 squared plus 82.1 squared, and then the same thing here, 1.5 squared plus 80.4 squared. Okay, so now we can calculate this. So we get this is 82.11 meters, and here we have 80.4 meters for 1 meters. So now the problem asks us to compare the arrow's displacements. You have to always look at the problem and see what exactly is it asking for. So we can see that the displacement of arrow A is greater than displacement of arrow B. So displacement A is greater than displacement B. And this is our answer for the first part of the question. Okay, so now we have the same problem as before, but this time instead of finding the arrow's displacements, we're going to find the max heights that they reach above the ground. Okay, so in order to find the max heights of these arrows, we can use equations for their vertical movement. So first we start with their velocities in the y direction. So for A, it's going to be 30 times sine 30 degrees, and for B, 30 times sine 60 degrees. And so 15 and 15 root 3 meters per second, respectively. And then we just use our kinematics equation, position final equals initial position plus initial velocity times change in time plus 1/2 times acceleration, which is negative 4.9 times change in time squared. And so now we have, basically these are just graphs of the arrow's movement. If you put this into like Desmos or something, you would get a parabola that would basically be what the arrow's path of movement. So in order to find the max height, we just find the vertex of the parabola. And if you remember your algebra 1 or 2 or whatever, then negative b over 2a is the x position of a parabola's vertex, which in this case would be the time at which these arrows reach their maximum height. And then we can just plug that time back in to their equation for movement to find the y value, or the position that the arrow was in at that time. So we can take out our calculator here. Okay, so for A, our B is going to be 15, and then divided by 2A, so A is negative 4.9, but in this case we have a negative in front of everything, so we can just cancel out the two negatives and do 15 divided by 9.8. So for the change in time of A, where the arrow reaches its max height, we have 1.53. And for B, let's see, we have 15 root 3, and then just divided by 9.8 again, 2.65 seconds. Okay, now we just plug these in to the original equations here. So for A, we have 1.5 plus 15
times 1.53 minus 4.9 times 1.53 squared. And so we have for A 12.998 meters. For B, let's see, we have 1.5 plus 15, 3 times 2.65 minus 4.9 times 2.65 squared, 35.94 meters. And now we have to, like the original question asks, we have to compare the arrow's max heights. So height B is greater than height A. Okay, so I didn't design a specific problem for this graph here, but I want to just take a look at it and ask a few little questions about it. So this is a velocity over time graph, and we can see there are two, these are supposed to be semicircles. I didn't draw them very well, but two semicircles here, and then velocity increases at a constant rate here, decreases at a constant rate here, and then stays constant here. So I want to first ask, where is the object accelerating and where is it decelerating? So if you want to pause for a minute or two and think about that. Okay, so acceleration occurs when an object's velocity is changing. That's just the broad definition of acceleration. And then you can say it's accelerating when its velocity is increasing and is decelerating when its velocity is decreasing. So technically the object is accelerating for all this time period up until here, because that's where its velocity stays constant. But we can say it's accelerating here because its velocity is increasing in the positive direction, and then it decelerates to, well, it decelerates all the way to here. And then decelerates on this time period here because its velocity is changing in the negative direction towards 0, and then it's accelerating again here in this time period. Let me just draw that. Okay, so it's accelerating again here in this time period because its velocity is increasing once again, going away from this time axis, and then once again it's decelerating here, and then its velocity eventually dips below 0. And then right here it's not accelerating or decelerating, the velocity is constant. So now I want to ask a bit of a trickier question. So where is acceleration changing in this graph? Where does the acceleration change? So you can pause and think about that for a minute. Okay, so if you're taking calculus, you know that acceleration is basically the concavity of a graph, of a position over time graph. And concavity is basically whether the graph is making a smiley face or a frowny face. Like if the velocity is slowly becoming less and less and less until it eventually dips below 0. But here we have a velocity over time graph and it's smiling and frowning. So that means that acceleration is also changing, because acceleration is the slope of this graph. And here we can see that even the slope is like gradually decreasing and decreasing and decreasing, and then increasing, increasing, increasing. So we can say acceleration is constantly changing pretty much for this entire period here, because it's accelerating a lot here. The slope is high, and then acceleration slowly dies down and down, and then it starts decelerating here, and then it starts, this is like the max, this is like the minimum velocity, I mean, where it's like at its most downward angle, and then acceleration starts increasing until velocity is shooting up like this. And then right here, acceleration is constant. Acceleration rapidly changes at these points, and you'll never see this in real life because acceleration and like velocity cannot just suddenly change that quickly where it creates like a sharp point on a graph. It'll be more smooth, and it'll look something like this. Like right here, it'll have like a smooth peak there. But yeah, acceleration, we can say, just for the sake of this problem, it just instantly changes at these points. And then acceleration is constant here, and there's no acceleration here. So now let's talk about how we can find the distance that this object covered. So if you remember, the position of an object can be found by taking the area under a position over time, a velocity over time graph, or a speed over time graph. So we could find the new position of an object by finding all this area up until some specified time. So if we say that like the initial position here is x, then if we want to find some position like maybe here or even just here, we can like just find the area under this curve up until that point. So if you were to find something like this on a test, then you would take the formula for a circle and then divide it in half, and then add that to this area down under it, maybe to find that area here. And then for here, you would take like this area of the rectangle and then subtract the area of the semicircle, and just use the area of a triangle for here, and so on, to find certain areas under this graph. And yeah, that's basically it. Thanks for watching, and I hope this was helpful, and good luck.